So I'm going to talk about the process of lithopanspermia, in particular the dynamical factors that drive it and constrain it. And a lot of this work that I'll specifically be talking about was with a graduate student of mine, Rachel Worth, who is now graduated and moved on. And it actually started as a code development project for her thesis, and got a little bit out of control into becoming a primary science project. Thank you. The basic idea is that we've just been talking about, that big rocks hit the surface, and there's a splash. And as Jay pointed out, you can get, moderately surprisingly, this is a very nice piece of work, you can get these gentle accelerations which eject material out into space. So what we're talking about here are cubic kilometers of material. We're talking about lifting the San Francisco Peninsula into space, gently, and fragmenting it. And we want to break it up into nice small pieces. And the basic assumptions here are that we can do this. We found them, so it must happen. That you make a lot of little pieces, but not too small. So you want pieces about this big. Those should have nice, pleasant interiors that have not been flash sheeted or shocked. Some of them, not all of them. Some of them become molten globules. And that they are shielded, so they can preserve at least frozen material for substantial amounts of time while in space. They have radiation shielding in particular. And they can land gently. You don't just need to get it up there, you have to get it back down again without flash frying everything and breaking it into little pieces. Oops, it's going backwards. There's a history of this, and we in particular leveraged off the work by Jay Melosh and Brett Gladman. It's actually the project started as a conversation with Brett I had about 10 years ago, and suggested that my student follow up on some of the concepts Brett had been working on. And there's been a bunch of work since then, in particular on extrasolar systems. A key point here is when you make these big splashes, you send out a spray of ejecta. Most of it falls back down again. That's bad. That's dinosaur killer stuff. But if the ejecta is energetic enough, if there's a spread of energies in the ejecta, some of it makes it to Earth escape velocity, and some range beyond that to higher velocities. So you essentially get two qualitatively different spreads of ejecta. You're going to get some ballistic ejecta that shoots off at high speeds. That's generally bad. Those tend to be the pieces that melted, and they tend to land not too gently. But there's always, as long as you're energetic enough, there's always a bit of ejecta that just barely makes it to escape velocity and goes into co-solar orbit around the Earth. And that is the material we decided to focus on as being maybe the most interesting for purposes. So we just did it. We took Chambers' mercury code, did some modifications to it, and this is the solar system. The wiggles are real. That's the eccentricity oscillation in the planets. And we're integrating Earth, Mars, and Jupiter, and looked at, this is a Mars ejection simulation. And you're looking at the secular orbital evolution of ejecta over mega years from the Mars system, and then we just track it. This is computationally insanely expensive. You have to do extremely precise integration for a very large number of objects, and you can't do a lot of approximations we use a lot of the time because that smears out the physics you're trying to track. But it works, and it seems to be a robust mechanism. Basically what happens is the co-orbital debris has small eccentricity, and that gets pumped by interactions with the surrounding planets, and some of that then random walks into planet crossing orbits, and then all of a sudden it's off. And the time scales for all of this is mega years. And we capped things at 10 mega years, although we did some test simulations to keep going for 100 million years, basically because there's a meme in the literature that you might keep biota viable for about 10 million years if everything works perfectly. Beyond that, you're pushing your luck. So we want to see what would happen in 10 million years. And this is what happens. This is now Earth ejecta, and this is the first million years of debris spreading out. And there's this diffusion in orbital space. And then after a few million years, you get resonances grabbing onto this diffusing debris, and all of a sudden it crosses planetary orbits, and you start slingshotting through the system, and you have opportunities for impact. Now, we made extremely conservative estimates. So the numbers I'm quoting are going to be underestimates, we hope, by at least 1 order of magnitude, maybe 2 orders of magnitude. And if you want to relax your assumptions and make more optimistic estimates for any of the parameters, the rates pretty much scale uniformly. First of all, we ignore the early dynamics. So we ignore the late heavy bombardment and the very heavy bombardment phase in the early system, because we didn't know if there was going to be any life then. If there's early life, all of this works much better. And we also put in basically a fudge factor, which is the fraction of rocks that are the right size that would not have been overheated. And then you have to worry about what fraction would actually contain biota. It depends on where you hit and how widespread it is. But we try to build that into the rates. Now, one of the interesting things, and this has been suggested in literature before, is a lot of the material that goes out and leaves the Earth and hangs around for a mega year or so, a large percentage of it actually re-impacts the Earth. And if it leaves Mars, it re-impacts Mars. This is peculiarly reassuring, because if you have a sterilizing impact, if you have a beyond dinosaur killer, something that's going to actually flash fry the entire planet, there is a significant probability that some biota is ejected and returns to the planet, hopefully gently, fast enough to reseed the planet. And this may be a escape from the sort of random catastrophes killing life whenever it gets established, by establishing refuges in space that then reseed the planet after being driven by the same mechanisms that kill everything off. The transfer rates between the terrestrial planets, so Earth to Mars, Mars to Earth, Earth to Venus, et cetera, are in the few percent range. That was actually surprisingly high. There really is a rain of rocks. And the numbers we're talking about here is about 1 billion pieces of rock. That's not a very small, not a very large number. This is a few cubic kilometers of rock. Over 10 million years. And we're estimating effectively, sort of implicit in the calculations, that impacts that are interesting in doing this, that contribute significantly to the rate, are happening every 10 to 100 million years. And it doesn't matter if you do intermittent pulses of stuff flying out or if you do a steady average rate. That does not affect any of the dynamics. About 1 part in 1,000 ends up going to the outer system. So most of it's stuck in the deep gravitational potential of the sun near the inner planets. And actually the goal of this was to find out if we could contaminate Europa and Titan. And the answer is you can just about. We found about a probability about 10 to the minus 6 of hitting the outer moons, which is in the range where there are a few impacts over a giga-year. But this is a conservative estimate, so it could be worse. And Mars does a little bit better than the Earth in this respect, about an order of magnitude better. So the solar system is vulnerable to cross-contamination, and we should be cognizant of that when we look for life in the outer system. And this ignores the possibility that life actually develops separately or originally on planetesimals. You get the same spallation reactions and spread. You have to crack open the egg if you make life in an asteroid or a comet. Okay, a few percent of the material also gets ejected into interstellar space at low speeds. We're talking hyperbolic speeds of a 10 to the minus 5 times the speed of light. So crossing times to the nearest stars are mega years, but that's not that different from the timescales we were looking at already. It's just a table of the outcomes, basically a table of probabilities. So now let's talk about other solar systems. This was actually, let's go back and do it again. This is a numerical simulation of planetary formation in the presence of migration. It's a set of research I played with Sean Raymond and Avi Mandel for a while. And you'll notice a lot of rocks disappear. They're ejected. So if there's stuff happening early on, you actually get a lot of ejection during the formation process in the early system, particularly if you have any migration by larger planets going on. And any sweeping of planetesimal or inner systems by high-mass planets leads to a large fraction of ejections. You can very easily, including in solar system formation scenarios where there was very little migration, there was clearly some, and there are scenarios, for example, where the Grand Tax scenario where Jupiter comes in an AU or two and then sweeps back out again. All of these things drive ejections early in the system. You can also drive out entire planets. You could easily have order 1 planet ejected per stellar system, probably not more than 10. That gives us a free-floating planet population of about 1 trillion in the galaxy. That's actually not that much. So this leads to an interesting conclusion, which a lot of people have been working on recently, which is that the solar system configuration really is not optimal for these things. You do much better with slightly lower mass stars, with closely packed resonant terrestrial worlds in the inner system, and you get fast, easy transfer in those systems. All the probabilities go up by a factor of several. And we keep coming back to TRAPPIST-1 in this conversation. TRAPPIST-1 is like a magic system for this. There are so many planets that are so tightly spaced, they may have multiple things straddling the habitable zone. You'd expect systems like that, if they develop life at all, if life is common, to completely cross-fertilize. And playing with this a bit, I think part of our problem is the solar system really is not the best place for life in general, at least not from a dynamic perspective. You really do better with these other systems. No, I'm stuck again. There we go. So we've seen the real systems from Kepler. These are theory systems. When you play with the various, particularly the migrating planet formation scenarios, you tend to end up with fairly closely packed systems. These are young systems. Some of them are going to continue evolving dynamically. The blue planets are water worlds. They have, in this particular approximation, you estimate that they have a very high percentage of volatiles. Yellow worlds are terrestrial-like. And you find, not uncommonly, that there are terrestrial planets in the habitable zone in near-resonant or resonant configurations, and quite often 2 or 3 of them. You also quite often find superterrestrials or low-mass Jovians internal to them. So the hot Jupiters can have terrestrial planets on the outside. And those also are interesting systems once you get to technosignatures and what you can do when you push life as opposed to waiting for natural processes. So we talked about a lot of this already. There's potentially a large population of free-floating planets. It's hard to get between them. Space is really big. It's hard to get a planet to another star. It's hard to get planetesimals to another star because star really isn't that big and space is enormous. You do better if you are in clusters, but clusters tend to dissolve and dissipate on timescales of megayears to gigayears. And so you get into a race between life getting established and life spreading between systems. I think there's an understudied area of this, which is that, for example, the solar system parent cluster is actually almost certainly in a cold dynamical stream. Gaia is going to pick that out. We're going to find the solar siblings. And the relative velocities between those stars are small. So we actually do the best transfer between our siblings, simply because they're even though they're spatially spread out from us, they're in phase space, they're fairly tightly packed close to us. The problem with hyperbolic entry is you come in at high speed and it's hard to capture. Now, Siraj and Loeb had a very interesting paper recently where they looked at the implications of Oumuamua as an interstellar visitor. And if you invert the numbers, if it's not a uniquely freaky, lucky accident, you get an extraordinary space density of those, 10 to the 15 per cubic parsec. That implies that they're entering the solar system at the rate of order 1 per month, if I run my numbers correctly. And any of them that come close enough to Jupiter, a few percent get captured in the solar system by the gravitational interaction with Jupiter. 3%, I think, was the rate they found. That implies a rate of capture of Oumuamua-like objects, order 100-meter class objects, where something like 10 to the 10 of them have been in the solar system over the history of the solar system. And they're fluffy, and they're not very big, so they land gently and break open when they hit the atmosphere. Ballpark estimate, actually ran this number this morning. I don't know if Abby's done this. Something like 100 of them should have hit the Earth. So if Oumuamua is representative, and we only look at the class of Oumuamua-like objects, then order 100 of them have hit the Earth during the history of the solar system and broken open and released their contents. Now, if any of them biota in them, we don't know. Maybe we should go and catch one and drill into it. But all of this can facilitate interstellar panspermia, not terribly well, but it's definitely not excluded, and there are channels where it can work. And of course, if you give it a push, you do even better. So just in conclusion, we do definitely transfer stuff between planets, no question about that. We do it in a way where, to our understanding, you should be able to transfer biological material. I don't know if we're talking nucleotide fragments, bits of DNA, flies in amber, little dormant water bears. The timescales between stars and planets are actually not that different, but it's very difficult to hit a star unless you're guided to them. We're told to be a little bit edgy here. And interstellar panspermia is possible given a lot of favorable assumptions on timescales that are not ludicrously prohibitive, and potentially testable in the next decades if we try to do Oumuamua type object interceptions, if Oumuamua is of a class rather than a unique object, and if we can get into them, break them open or drill. And I think that is where I am going to stop for lunch.
We got time for a couple. Start with you.
Hi. I just want to know, when you're doing your calculations of ejecting things from Mars or Earth, first, you're assuming these are the early Mars and Earth, or no?
No, we just assume they're balls with gravitational potential and surface.
Okay. So
Everything else we pass off to other researchers.
I see. But atmospheres have to be considered. And what happens to the flux because of the presence of an atmosphere, both on the body from which it's being ejected and on the body that it's aimed at? So yes. Did you consider that?
So roughly speaking, Earth and Mars atmospheres don't matter.
But early on in the early solar system, Earth might have had a more substantial one. Mars might have had one too.
So there's the recent results, the raindrops on South African rocks result that suggests very strongly the Earth never had a very thick atmosphere.
Oh.
So no, we did not consider, for example, an early Earth having a 100-bar atmosphere. Also, we explicitly excluded the early Earth because we wanted to be in the safe zone where we are looking at after development of life only, with the implicit understanding that if you want to go back to the early period, you just scale everything up. If you have a very deep atmosphere, yes, then it's an issue, and what it'll do, it'll cut your tail of ejecta, and more stuff will fall back down.
So you used a realistic flux of debris onto the Earth, or did you account for the fact that there's, that tails off with time? So if you're waiting for life to evolve, you're using the flux.
Oh no. So the integral over the flux of impactors on the Earth can be done independently of all the rest of the calculations.
Can be done what?
So you look at what happens in a single impact, and then to average over the solar system history, you just pick your own time profile and size profile of impactors and integrate over it. It's not limited to any one specific rate of flux of impactors.
One final one.
Hi, Robert Kennedy, Institute for Interstellar Studies. My colleagues are here and co-authors. We funded the paper that just came out in AppJ by Marshall Eubanks. It's called Interstellar Dandelions. So when you say fluffy, it's really fluffy. Like fluffy means Fluffy is actually maybe 3 orders of magnitude less density than the best aerogel human beings have ever made. And that's why it can just slowly enter. It gets slowed down long before it hits real atmosphere, and it just gently drops in. So I'll send you the paper, and we've got the same order of magnitude results as you with 10 to the 15th. And in those dynamical streams, 2 kilometers a second maybe, velocity dispersion in those. Paper makes predictions on where to look for future Oumuamua interstellar lint.
Okay. 10 to the 15 was from Avi's paper, or Suraj's paper, but I rerun the calculations just in case. So yeah, I think that's a robust number. If Oumuamua is representative of a class of objects, which I don't think we were lucky enough to find a freakishly unique object like that. And that is interesting.
Thank you.
Yep, lunchtime.